Hello everyone, today I will present our work. This work is done by Liu He when he interned at Amazon. Here's the outline of my presentation. VLMs have broad applications in many areas, but to use them effectively, they require accurate recognition of camera-object relations. However, we found that current VLMs have significant weaknesses. The first one is object orientation. In these two examples, the VLM models cannot tell the correct object orientations for the turtle and diver. Second, we focus on camera viewpoint, which is the elevation angle of the camera towards the object. We tested GPT-4o and find that it failed to correctly identify the camera viewpoint for both of these images. The third weakness is camera shot, which is the relative distance from the object to the camera. As you can see in the example, even though GPT-4o knows the definition of close-up, medium shot, and non-shot camera types, it still gives wrong answers about the actual camera shots in the images. We also try to search for datasets containing this information, but we find that these camera object relations are generally missing in the current VLM datasets. We propose a pipeline G to generate VLM dataset D in order to maximize the VLM prediction loss and preserve quality. Most current models that want to achieve some 3D awareness leverage deep learning methods like depth estimation and segmentation to extract information from view images. For example, spatial RGPT and spatial VLM use depth segmentation and camera calibration models to produce dense predictions. However, these methods rely on the accuracy of the downstream models. Second, there are papers focusing on text-to-image generation using stable diffusion. They generate text prompts for specific tasks and use these prompts to create corresponding images. However, the generated images often have quality issues and artifacts, and more importantly, it's hard to control the geometry. Third, there are approaches in the robotics community that use fully synthetic CAD models like NVIDIA Omniverse and Kubrick. However, these datasets contain very simple and basic objects with limited scenes. There's a significant domain gap between these synthetic images and real-world images. We also analyze the limitation of both real and synthetic data resources. So can we leverage both sides to boost VLM camera object relation recognition? Our core idea combines three components. First, accurate 3D geometry to get ground truth relations. Second, photorealistic image generation via stable diffusion-based image generation. Third, diverse dataset distribution through versatile text prompt generated by LLMs. Our contributions include a generation pipeline for unlimited 3D aware VQA dataset, the ultimate 3D dataset benchmark for VLM camera object relation recognition, covering orientation, viewpoint, and shots. And finally, fine-tune VLMs that outperform SOTA models in camera object relation tasks. Our framework has four components. First, 3D visual prior rendering. Starting from 3D assets, we import them into Blender and post them across various camera object relations. We render multiple visual priors, depth maps, candy edges, normal maps, and use them as conditions for multiple control nets in the stable diffusion pipeline. Second, diverse image description generation. We give GPT-4o instructions to generate visual prompts including background context and object appearance descriptions. These are used to guide the stable diffusion image generation. Third, control image generation. We utilize DMs to generate photorealistic images given comprehensive visual prior. Fourth, text instruction generation. We utilize GPT-4o as a LLM to generate QA pairs on camera object relation for visual instruction tuning. For the 3D rendering step, we use Blender as our renderer. we define the following camera object relation parameters: elevation angle, azimuth angle, and distance between object and camera. Given these parameters, we render multiple visual priors from the 3D assets, RGB images, depth maps, candy edges, and segmentation masks. These multiple priors will collectively serve as conditions for the control image generation in the next step. For diverse image description generation, we give GPT-4o a system prompt and a category of the object. GPT-4o then generates appearance descriptions and background context descriptions. For example, given snowmobile as input, GPT-4o generates the following example output. The diversity and rationality of these descriptions directly influence the image generation quality. For the control image generation, we use multiple control nets stacked on the SDXL backbone. The depth mask and candy edge from the 3D rendering, together with the test prompt from GPT-4o, are fed as conditions into the multiple control nets. This approach generates photorealistic images that preserve the original camera object relations from the 3D rendering. The depth prior is crucial for avoiding depth ambiguity, and the candy edge prior helps maintain the object's structure. Once we have the generated photorealistic images and the corresponding ground truth camera object relations, we generate VQA pairs. We classify the object orientation into two A types, camera viewpoint into 3 types, and camera shots into 3 types. These image test pairs form the core of our ultimate 3D dataset and benchmark. Now let's move to our experiment. Here is the experiment details for the ultimate 3D dataset. Specifically, we selected 100 categories with explicit facing orientations from ImageNet 1D. For example, we excluded objects like bottles that are essentially symmetric with no explicit orientations. We generated 240,000 VQA pairs covering all 3 camera object relations types. More importantly, there's no dataset bias. All the angles are uniformly distributed. Here are some example images from our Ultimate 3D dataset. The images maintain both accurate camera object relations and photorealistic quality. Each image has corresponding VQA pairs about the object's orientation, camera viewpoint, and camera shot type. For evaluation, we created the Ultimate 3D benchmark with a total of about 6,843 VQA pairs without distribution bias in our benchmark. For the fine-tuning experiments, our target models are Lava 1.5, 1.6 plus Llama 3.2 Vision. We fine-tune all models on our Ultimate 3D dataset for one epoch. We compare the fine-tuned models against the original models and commercial SOTA models like GPT-4o to show improvements. This table shows comprehensive results on the Ultimate 3D benchmark. Key findings are: our fine-tuned models achieve the highest performance across all capabilities, object orientation, camera viewpoint, and camera shots, on both synthetic and real image space. More importantly, fine-tuned models significantly outperform commercial SOTAs at the same time. We also observed that mixing Ultimate 3D with Lava Instrust 665K when training Lava 1.6 13 billion maintains VQA V2 performance while improving camera object relation accuracy. Here are visual comparisons between our fine-tuned Lava 1.6 13 billion and GPT-4o on the Ultimate 3D benchmark. On the right, GPT-4o gives wrong predictions even for the cases that are very simple for human. Our fine-tuned model on the left correctly identifies object orientations, camera viewpoint, and camera shot type. Here's another visual comparison on the MMVP benchmark with real images. For example, a sport cut in the image, commercial model gives wrong answers for this simple case, while our fine-tuned model correctly identifies the camera object relations. This further validates that the improvements from our Ultimate 3D dataset generalize well to real-world images from external benchmark. Conclusions. First, we introduce a data generation pipeline for high-quality image text pair generation focusing on three types of camera object relations. Second, we provide the Ultimate 3D dataset and benchmark for these three tasks to benefit both fine-tuning and evaluation. Third, we show that VLMs fine-tune using our Ultimate 3D dataset beat SOTA commercial models, including GPT-4o, by an average of 33.4% accuracy. Future work includes extending to multi-object relations and improving numerical prediction capability. Thank you.